Hello friends, in today's question, two disks A and B are mounted coaxially on a vertical axle. The disks have moments of inertia I and 2I respectively about the common axis. Disk A is imparted an initial angular velocity 2 omega using the entire potential energy of the spring compressed by a distance x1. Disk B is imparted an angular velocity omega by a spring having the same spring constant and compressed by a distance x2. Both disk rotates in clockwise direction. So here we are supposed to find out these three things. First is the ratio of x1 and x2. B part is disk B is brought in contact with disk A. They acquire a common angular velocity in time t. The average frictional torque on one disk by the other during this period is. And in part C, we are supposed to find out the loss of kinetic energy during the B process. So we are given two disks A and B and they are mounted coaxially. Okay, let us suppose this is A disk and they are mounted coaxially, and this is disk number B. So this is disk A and this is disk B. Moment of inertia of disk A is I and moment of inertia of disk B is 2I, and angular velocity of disk A is 2 omega and angular velocity of disk B is omega. Okay, and they are being you can say the angular velocity is imparted by the use of spring. The spring that is connected with disk A is compressed by the distance x1 and having a spring constant k, and the spring which is connected with with disk B is having a spring constant of x2, is compressed by x2 and it has a spring constant of k. Okay, so spring constant in both the cases is same, while the compression for A is x1 and for B is x2. So let us solve it for first part, that we have to find out what is the ratio of x1 and x2. So for part A, we can find out that the kinetic energy of the disk A, or when it is rotating, and then we are going to find out the energy stored in the spring, and then we are going to equate them for respectively for disk A and disk B independently, separately, and then we are going to solve it. So we know the formula that kinetic energy of rotating disk let us suppose is given as E kinetic, and that will be equal to half moment of inertia omega square and energy stored in the spring. Energy stored in the spring, let us suppose that is given as E spring, which will be equal to half k and x square. So let us modify these two formulas for disk A as well as disk B. We can say for disk A, moment of inertia is given as I. So moment of inertia is our I, and we have angular velocity as moment of inertia for disk A, let us suppose it is given as IA, which is equal to I, and angular velocity let us suppose it is given as omega A, and which is equal to 2 omega. Therefore, now we are going to equate the energy stored in the spring equal to the kinetic energy of the disk, respectively for A as well as B. So we can say that energy imparted by the spring to disk A will be equal to kinetic energy of disk A, and the energy imparted by the spring will be equal to energy of the spring. Energy stored in the spring is half kx square. So we can write this as half k x1 square will be equal to, this will be equal to half moment of inertia of A and angular velocity of A. So this will be equal to half moment of inertia is given as I and angular velocity is given as 2 omega. So we can write this as half k x1 square is equal to half I 2 omega. Let this be equation number 1. Similarly, we can say for disk B, its moment of inertia, let us suppose, is given as IB, and IB is 2I, and we have angular velocity, let us suppose, is given as omega B, and this is equal to omega. So once again, energy imparted by the spring to disk B is equal to kinetic energy of the disk B. Energy imparted by the spring to disk B is equal to kinetic energy of disk B. So energy imparted by the spring to the disk B will be equal to energy stored in the spring, which is equal to half k x2 square, and kinetic energy of the spring will be equal to half moment of inertia of the disk B multiplied by its angular velocity square. One second, yeah, I made a mistake here. This should be equal to square, and this square as well as this square. So substituting the value, this will be half IB is 2I and angular velocity is omega and its square. So therefore we can write that half k x2 square is equal to half multiplied by 2I multiplied by omega square. This is equation number 2. So dividing equation 1 by equation 2. Equation 1 dividing by equation 2. Equation 1 left side is our half k x1 square divided by half k x2 square is equal to, and for the right side we have half I multiplied by 4 into omega square divided by half multiplied by 2I into omega square. So half k and k cancel out. In this side I goes with I, omega square goes with omega, and this 2 goes with this 2. So this is equal to 2. So therefore we can say that the ratio of x1 upon x2 is equal to square root of 2. And if we check the option available to us, we can say that option C is the correct one. So you can say option C is correct. Now let us solve for B, and it says that when B is brought in contact with disk A, they acquire a common angular velocity in time t. The average frictional torque on one disk by the other during this period is. So we solve for part B, and in part B we are going to find out the initial angular momentum and final angular momentum, and then we are going to equate it and solve for the frictional torque, average frictional torque rather. Okay. So we can say that initial angular momentum, in the initial will be, both the disk will be separate. Okay. So let me draw the diagram here. So initially both the disks are separate. So this is disk A and we have disk B. So this is disk A and disk B, both are separate, having the moment of inertia I, angular velocity 2 omega, moment of inertia 2I, and angular velocity omega. And in the final condition, these two are brought together. Okay, so they will be something like this. Now after some time t, obviously both will be rotating with the same angular velocity. So we are saying let that angular velocity is given as omega f. Okay, so here we have A is in contact with B. So therefore this is our initial condition, and this is our final condition. So let us use the angular momentum first of all for initial, then for final, and then we are going to further solve it. So let us find out the initial angular momentum for disk A. Initial angular momentum for disk A will be equal to, let us suppose, is given as LA, and LA will be equal to moment of inertia of A multiplied by its angular velocity, and moment of inertia for disk A is given as I, and angular velocity is 2 omega. Therefore our LA comes equal to 2I omega. Similarly, we find out initial angular momentum of disk B. Let us suppose that is given as LB, which will equal to moment of inertia of B multiplied with its angular velocity. Moment of inertia is given as 2I and angular velocity is omega. Therefore we get LB is equal to 2I omega. So we can say that total initial angular momentum, total initial angular momentum, let us suppose that is given as L initial, which will be equal to LA plus LB. So we get L initial will be equal to 2i omega plus 2i omega, which comes as 4i omega. So we found out the total initial angular momentum, and now we are going to find out the final angular momentum. We say final angular momentum after each disk after the disk have common angular velocity, which is equal to omega f. So therefore we get L final is equal to moment of inertia of A plus moment of inertia of B multiplied by final angular velocity. So IA is given as I and IB is 2I, which will be equal to omega f. So therefore we get L final will be equal to 3I omega f. Now using conservation of angular momentum, conservation of angular momentum, L initial is equal to L final. L initial is equal to L final. So L initial we have 4I omega. L final we have 3I omega f. So here I cancel with I. So therefore we can write that our omega f is equal to 4 by 3. Omega f is equal to 4 by 3 omega. So this is the relationship between the individual, you can say, angular velocity to the final angular velocity when they are rotating with the common angular velocity, that is omega f. Next, we are supposed to find out the torque due to friction. Okay. So we can say that torque due to friction. So because of this torque, which will be because of the friction, there will be, you can say, the change in the angular momentum. Okay, and this change of angular momentum we are going to use to find out the respective solution. So here we can say that change in angular momentum for each disk is due to frictional torque, is due to frictional torque. Let us suppose that is given as tau. Therefore, let us find out for each disk. Therefore, we can say change in angular momentum, change in angular momentum, first of all for disk A. For disk A, the change in angular momentum, let us suppose, is delta A. This will be equal to omega f minus I into, IA, and now it will be having a, you can say, the common moment of inertia. Okay, so let me rephrase it. Delta LA, that is change in angular momentum, will be equal to I omega F minus I into 2 omega. So we get LA will be equal to, taking I as common, omega F is equal to, we already found out the relationship with omega, so this will be 4 by 3 omega minus 2 omega, and this comes as minus 2 by 3 I omega. Similarly, so we found out for disk A. Similarly, we can say for disk B. For disk B, delta LB will be equal to, moment of inertia is given as 2I, and this is our omega F minus 2I multiplied by omega. So we get change in angular momentum for B will be equal to, taking 2I as common, omega F is 4 by 3 omega minus omega, and this comes as 2 by 3 I omega. So now we are supposed to find out, that is your average angular, average frictional torque. So we can say average frictional torque for disk A. Let us suppose that is given as tau average A, and it will be equal to change in angular momentum of A divided by time. This comes as minus 2 by 3 I omega divided by T. Or we can write it, tau average for A will be equal to minus 2 I omega divided by T, 3T rather. Similarly, we can write for disk B. For disk B, we have tau average for B will be equal to change in angular momentum of B, and time, here also it comes 2 by 3 I omega divided by time T. So we get average for B is equal to 2 I omega divided by 3T. So in the question, we are supposed to find out is average frictional torque for one disk by the other during this time period. Okay. So from here we can say the average torque of disk A and B magnitude wise is same. Only thing is that the direction will be opposite. So therefore the option that is available to us is option number A. Okay. So option A is the correct option. Option A is correct. And in the last part, that is in C part, we are supposed to find out the loss in kinetic energy. So in C, we are supposed to find out the loss in kinetic energy. So in this case, we are going to find out the total initial kinetic energy and total final kinetic energy and find out the loss. So we can say that total initial kinetic energy will be equal to, let us suppose that is given as K initial. This will be equal to kinetic energy of A plus kinetic energy of B. And we are going to first of all write kinetic energy for A. So kinetic energy of A will be equal to half moment of inertia of A and its angular velocity. So this equal to half I, and angular velocity is given as 2 omega and its whole square. So this comes as 2I omega square. Similarly, the kinetic energy for B is equal to half moment of inertia for B and omega B square, and we get half moment of inertia of B is given as 2I multiplied by omega square, and this comes equal to as I omega square. Therefore, kinetic energy initial, K initial, will be equal to 2I omega square plus I omega square, and this comes as 3I omega square. And now we are going to find out the final kinetic energy. Final kinetic energy, which basically means after the disk have reached a common angular velocity, that is omega f. After the disk have reached a common angular velocity, and that angular velocity is omega f, which is equal to 4 by 3 omega. And loss in kinetic energy, so we can say the kinetic energy of disk A, let us suppose, is given as Ka prime, let us suppose that given kinetic energy A prime, and that comes equal to half I omega square. So it becomes half I 4 by 3 omega whole square. So we get kinetic energy of A is equal to, this will be coming as 8 by 9 I omega square. And we are supposed to find out, similarly, we get kinetic energy for disk B. Kinetic energy of disk B, and that is given as kinetic energy Ke prime for B is equal to half moment of inertia is given as 2I and omega f square. So we get Ke prime B is equal to half multiplied by 2I omega f square will be equal to this will be 16 by 9 omega, and 2 goes with 2, therefore we get kinetic energy prime is equal to 16 by 9, square is left, I omega square. So we get total kinetic energy final final, let us suppose given as K final, is equal to kinetic energy of A plus kinetic energy of B. So we get K final is equal to 8 by 9 I omega square plus 16 by 9 I omega square, and we solve it, we get K final is equal to, this will be coming as 8 by 3, and this will be 24 by 9 I omega square, and this goes by 3 and this goes by 8. So we get 8 by 3 I omega square. So we found out the total kinetic energy final as well as total kinetic energy initial. So loss will be equal to their subtraction. So we can say that loss in kinetic energy will be equal to, let us suppose that is given that delta Ke is equal to kinetic energy initial minus kinetic energy final. So we get delta Ke, kinetic energy initial is our 3I omega square minus 8 by 3I omega square. So we get this as 9 minus 8 divided by 3I omega square. Therefore, the loss in kinetic energy will be equal to 1 by 3I omega square. So the option available to us is option number B. So option B is correct. Option B is correct. Therefore, this completes the question. Thank you.